All right, 1.7 is about inverse functions, and these are things that you've learned about in Algebra 1, Algebra 2, and so this is kind of just, we're going to start with a review. Inverse functions, there's three ways you can find them: numerically, graphically, and analytically. All right, so first of all, numerically, two functions are inverses of one another if the x and y of one function corresponds to the y and x of another, meaning f of x of 1 is equal to f. So here's what I mean. If f of x has this point, then the inverse will have 3, 2. The x and the y switch places. 0, 5. Then the inverse would have 5, 0 as a point on its function. Okay, so that's what this means here, is that numerically those points would be the reverse of one another. Okay, inverses of one another. Now, graphically, you know the two functions are inverses if they are symmetric along the y equals x line. Okay, that's just the diagonal. The y equals x line looks like this. So if you can imaginarily fold along that line and the two shapes match, then they are inverses. All right? And then analytically, the composition results in an identity function. And we'll talk more about this later, but basically it says if you plug one function into the other, you make a composition, and you solve it out algebraically, you get x. And the reverse. And then you plug the original function into its inverse, solve algebraically, you get an x as well. All right? So let's think about this for a minute. Let's just draw a graph, and this will be y equals x squared. Okay, this is just your basic parabola. Okay? Basic old parabola. And let's say I have this point right here at 2, 4. Okay? Now remember, I told you that it would be symmetric along the y equals x line. So I'm just going to dot that line in here. And we're going to pretend that we fold that parabola across the line. Well, what would happen if we did that? If we did that, we would get a parabola going this direction, right? And what you would find if you could trace this, you would find that the point 4, 2 is on that inverse function, right? So that's what we're talking about here graphically, what's going on. Let's try another one. Let's say I have the function, the good old cubic function, y equals x cubed. All right, we know that that does this thing. All right, and let's say I have the point 2, 8 here, and the point -2, -8, okay? Now, if I fold along that imaginary line, that y equals x line, okay, where's that? Well, that's like right here. What's going to happen? Well, your inverse function would have a point way out here at 8, 2. Okay, so it would do this. And this one would have a function at -8, -2. Okay, so that'd be like way out here. It would curve like this. Okay, so you can see it's going to twist it up along that inverse line. So that's what they would look like graphically. If you could see the points, they are just inverses of one another. Okay, interchanged coordinates. Now, another thing you can do is what's called the horizontal line test. And it says if every horizontal line intersects the graph of a function at most once, then the inverse graph is also a function. Okay, it has to be a function to start off with. And if you look at it, like our cubic, and we draw a horizontal line, it only hits at one place, then the inverse of this is also a function, which we just saw. It does this thing. Okay, that is still a function. Now, what wouldn't pass that is our parabola. Okay, if you think about your parabola right here, if you draw a horizontal line, it crosses 2 times. So the inverse of this is no longer a function, which if you go back to what we did before, right here, this red one is not a function. It does not pass the vertical line test. All right? So they go hand in hand. But horizontal line test is the one that is uniquely for inverses. One-to-one function is a function that passes the horizontal line test. All right? That's what we call it. Now, the types of problems you're going to see have to deal with all these different versions of finding inverses. So let's start with this first type. Find the inverse algebraically, then prove algebraically that f and f of -1, the inverse, are inverses. Okay? So to find it algebraically, there's several steps you need to walk through. The first thing that you would do is replace f of x with y and leave the function alone. And then you exchange your x and y, flip them, and now our goal is to solve for y. Okay, so I'm going to rewrite it up here where I have a little more room. Okay, so the first thing I'm going to do is multiply both sides by 5. Remember, that's 5 over 1. So these 5s will cancel out, and now I have 5x equals y. Well, that was my goal, solve for y, so I'm done. Now I replace that y, I'm just going to rearrange, with a negative f -1 of x. That is the symbol for inverse, so we read it inverse of f equals 5x. Okay, so here's our function, our inverse function. Then it says to verify that these are inverses. So I'm going to take my original function and my inverse function and plug them into one another and see if I get it. Okay, so we're going to do it 2 ways. We're going to plug the first one in here. So I'm going to take 1/5, and instead of x, I'm going to put times 5x. Okay, the 5's cancel, and what's left? Well, x is left. Now, what about over here? If I plug f of x into this, okay, I'm going to have 5 instead of x. I'm going to replace it with what's over here, all of this. So 1/5 x. Remember that 5 is over 1. So again, the 5's will cancel out, and it equals x. So I've proven that the compositions of them both equal x. I've verified this is a function. Now, show algebraically that f and g are inverses. It's the same thing we just did. They're just giving you the inverse. You don't have to find it first, right? So I need to find f of g of x. So I'm going to take the f function, and where x is, I'm going to take the f function, but instead of putting x, I'm going to put all of g of x in there. So whatever x is, I cube it, right, according to f. So I'm going to take all of this and plug it in. All right, the cube root of x cubed. Well, when the powers match, they cancel out. So I get x, simple enough. F of g of x equals x. Now we reverse this, g of f of x. We're going to take the g function this time, which is the cube root of whatever x is. Well, now I'm going to plug f of x in there, and I get x cubed. Again, if the powers match, they cancel out, and g of f of x is going to equal x. Okay, so we've shown algebraically that they're inverses by getting them both solved for x. Okay, example 3, same thing. All right, I'm going to start by doing f of g of x. So I'm going to take the f function, which is the square root of something minus 4, right? Then I plug all of g in there. So x squared plus 4 minus 4. Well, those 4's cancel one another out because 4 minus 4 is 0. Then I have the square root of x squared. Well, again, square root of x squared is just x. So f of g of x equals x. Now let's switch it and do g of f of x. So the g function says whatever x is, I square it and add 4. So I'm going to take the f function and plug it in there. So I get square root of x minus 4 plugged in. When you square root, the square root goes away. So I have x minus 4 plus 4. Negative 4 plus 4 is 0. So this just leaves me with x. So because both of these solved for x, I've shown algebraically that these are inverses of one another. Now, last part. A function is one-to-one. Two inputs, A and B, you're going to get the same output, which means that A and B had to be the same, okay, because it was a function. All right, now, how do we do this? Well, let me show you how to do it. The goal is to just get down to A equals B. So here's how you're going to handle this. Now, the directions say determine whether it's one-to-one, verify graphically, and if it is one-to-one, find its inverse. Okay, so let's just do the one-to-one part first. So you're going to rewrite your equation one time with A and one time with B and set them equal. So f of A equals f of B. All right, so we're going to plug in A. We get the square root of A plus 1 equals the square root of B plus 1. All right, if I just start to solve this, I get subtract 1, those go away. I have the square root of A equals the square root of B. Well, I'll get rid of square roots, we square them. So now I just have A equals B. All right, so I've shown that A equals B, whatever it is, right? That works. I've shown it. Now, if I go to graph, okay, does it pass the horizontal line test? Yes, it does. Okay, so now I know that it does have an inverse. So I'm going to find my inverse algebraically. Okay, just like we did before. I'm going to rewrite the original function just so we have it. We said before you have to replace this with y. Flip your x and y. And solve it for y. So now I need to subtract 1 from both sides. So x minus 1 equals the square root of y. Get rid of the square root by squaring both sides. So then I would have y equals x minus 1 squared. And I replace y then with the inverse symbol. Okay. So now we've done all our steps on example 4. Okay, we've shown algebraically it's one-to-one. We verified it graphically, and then we found the inverse. Okay. Now example 5. Come back up here. Let's do the same process. We need to find out if f of A is equal to f of B, because that would mean A and B are the same. All right, so rewrite your function with a's, a to the fourth plus 2a squared minus 6. That equals b to the fourth plus 2b squared minus 6. Okay. So now we just start to solve this. So plus 6 plus 6, so it makes our 6's go away. All right, now we could keep solving and all this stuff all the way down if you wanted, but what I want you to catch is this. The functions are basically, they look the same, right? And we could keep going on down, but notice that both of the powers are squared. And if you square a negative number, don't you get a positive number? So what's going to happen here is I could get A equals B. That does work, right? It would work here. But wouldn't negative A equals B work as well? Because if I plug in a negative A, it's going to make it squared because of the even powers. As a result, that works as well. What if it was A and negative B? Well, same thing would happen here. It would become positive because I have negative powers. So the fact that all three of these work means this is not one-to-one. Okay? It can't work if there's more than one option. So I don't need to go further. I don't have to do the horizontal line test. But if you did, let's just see what happens, and it'll prove that it's not. Okay? So let's come up to our calculator and type this puppy in. So look at that. If I draw a horizontal line, I'm going to hit it twice, which means it's not an inverse. There's not an inverse function. Okay? So it's not one-to-one. There is no inverse function. That's what that means. Now let's try the next one. All right? So again, I want to see if f of A is equal to f of B, meaning A and B would be the same. So I rewrite the function with A. and I rewrite the function with b, and I start to solve this, okay? So I'm going to multiply both sides by 5 over 1. The 5's will cancel. Then I have 3a plus 4 equals 3b plus 4. Well, if I subtract 4's, now I have 3a equals 3b. Divide by 3, then I get a equals b. Bam, it works. So if a is negative, b is negative. If a is positive, b is positive. There's really only one way it works, okay? If a is negative and b is positive, it won't work. It will not work. So this one is 1 to 1. So if we graph this, verify it by graph. All right, can it pass can it pass the horizontal line test? Yes, it does pass. So there should be an inverse function. So now we do part 2, and we find the inverse function. So remember the original, 3x plus 4 over 5, okay? So again, we rewrite this as y equals 3x plus 4. And then we swap our x and y. So now I have x equals 3y plus 4 over 5. And my goal is to solve for y. So I'm going to start by multiplying both sides by 5 over 1. These 5's cancel out. So now I have 5x equals 3y plus 4. Subtract the 4. Divide both sides by 3. And then that'll be y equals 5x minus 4 over 3. But we need to put it in inverse notation. So we say f of negative 1 of x, that's inverse, equals 5x minus 4 over 3. All right, that's how you do it. That's how you prove one-to-one algebraically. Don't let it intimidate you. We'll work on this in class if you got questions.